Good afternoon. Let's get started. Next week, we do not have a speaker, but we have a very special event that we have once every semester. It's the Energy Open House, where different student groups, faculty, research staff just come in, hang out, have pizza or sandwich, soda, and just talk about all things energy on campus and outside of campus for that matter. So if you happen to be around, please come in and bring your friends. It's really a special event. We try to make it special. It's a great pleasure, really, to introduce our speaker today to you, Professor James Wesley, who is an associate professor and chairman of the Department of Architecture at the University of Wisconsin-Milwaukee. Jim has been the former president of the Society of Building Science Educators and is currently the PI of the Carbon Neutral Project, which he's going to talk to us about today. He's also the founding member and former president of the Wisconsin Green Building Alliance. When I looked at his research and teaching portfolio, it's really very fascinating. The different components that he has really sound very exciting. And for example, creation of extreme case healthy environments, documentation of thermal performance of existing buildings, resource conserving materials, and very interesting daylighting in architecture. This is something that we've heard about a little bit from Professor Matt Pacus, maybe 3 or 4 semesters ago at the Symposium. Some of you may have been around at that time. And all of this, as you can imagine, really brings a new dimension. And most of the time when we think about energy, it's like the cars, the oil and gas, the solar, the fracking. Buildings, architecture has a huge, huge role to play. And this has huge implications for energy efficiency and human health. And we are so excited that Jim with us here today. Please join me in welcoming Jim.
Thank you. Okay, that's on. Thanks, everybody. Let's see. I'm going to see if I can indulge myself and get this thing to neutral. Well, maybe not. Yeah. So I'm going to be talking about carbon neutral design, and I'm just curious, what are people's interests, background, skills? Engineering, architecture, other fields? Architecture. Good. Engineering. Good. Anything else? Policy. Well, I'm going to talk about, it's a bit of a postmortem, and it's a bit of a kludged together lecture, 2 different projects that have been mining the same general vein. The Carbon Neutral Design Project, which is what I was invited here to talk about, really didn't quite dive. It went into a deep stasis when the economy fell apart. It was funded by the AIA, and everybody we were working with at the AIA was no longer working at the AIA. So I'm going to talk about a project that hasn't really realized its potentials. It had very ambitious complicated goals, and it had very ambitious, simple goals. And what I want to try to do today is talk, at least in an introductory way, that's why I called it a primer, on some of the simple ways of thinking about carbon neutrality. Because if you're all engineers, my message to you is that if you're going to be working with architects, you need to communicate to them that it's their job to reduce the loads of these buildings down to the point where you can engineer them to carbon neutrality, because it is a design problem. It's not fundamentally an engineering problem. Sorry to tell you that, but I think this knowledge should empower you. I want to show a short video. This is going to set the stage a bit. It's a little bit of a diversion, but it does talk about the building that was at the heart of the Carbon Neutral Project. This is the Aldo Leopold Legacy Center. How many people have heard of Aldo Leopold? Only 2 of you. So Aldo Leopold was a great naturalist, really. In some versions of events, the father of American environmentalism. He taught at Madison. This building is built outside of Madison on a farm that he reclaimed. It was a Dust Bowl property in the Sand Counties of Wisconsin. So it's a book called The Sand County Almanac. And if you haven't heard of that, it's a great piece of American literature on environmental thinking. So this building is built to honor his legacy. And I just want to play you this brief video that was thrown together to try to explain some of the ideas of the Carbon Neutral Project. And the sound should come up here in a minute.
Part of the limitation that architects have is their fee only goes as far as the completion of the building construction. So they have no way of learning, getting much feedback at all from how a building operates. It's just the economic structure of what we have to deal with. The case study, and especially the work of Mike Utzinger, and the ability of the university to research how a building operates is utterly valuable to us as a student. So the case study is a direct feedback loop to the next building that we design.
The Aldo Leopold Foundation had a client who requested that the design team design a carbon neutral building, and we had to define what that was. And the process that we did in doing that was we said that the building had to be net zero. That is, the energy that we generate from the sun over the year for the building had to at least equal the energy that would come in from the grid. That is, what we produced had to equal the entire building's energy demand. And we depended upon our knowledge of other high-performance buildings to have an idea of what to do. Basically, we looked at a building that was designed by William McDonough, the Woods Hole Research Institute, which requires about 5 kilowatt hours of electricity per square foot of building per year. And at the time, that was the highest performance building that I was aware of in the U.S. And I said, okay, if we can design a building that can achieve that small and energy footprint, we can meet that entire energy demand with 3,000 square feet of collector for a 10,000 square foot building. In the design process, used energy simulation to validate the design. We came up with a design that met, in design terms, that energy goal, and then that became the basis for building a building that was net zero. And it took the knowledge of other measured buildings to understand what buildings could achieve. And so now this building, the Aldo Leopold Foundation building, the Ideas building, which was designed by EHDD, that was one of the buildings here, are now examples of net zero. And most of them are using this approach, understanding what your goals are for energy use, and then understanding what your potential is for energy generation and balancing the two of those.
Strangely enough, this project had very few surprises because there was such a fantastic team of people modeling and then checking the feedback from the building as it was used. We have to have more data on the kinds of things that people plug into the wall that you couldn't have foreseen. So there's got to be, if we can measure enough buildings to see the difference between what was assumed to be plug load and what actually was a plug load, we'll have a better idea to build that amount of energy use into the model. We may then need more insulation, we may need more PV supplied, we have to balance the amount of energy produced with the amount of energy used, so that's a key part of the formula.
The Aldo Leopold Foundation ended up not achieving net zero and carbon neutrality, but being close enough that we are fairly confident that by the second year or third year we'll be able to achieve it, just in terms of educating and working with the foundation on operating the building and even making some adjustments on some of the pieces of equipment that are in the building. And all of that is really that feedback loop coming back, or that knowledge of how buildings really work, and then moving forward in the next designs to really achieve carbon neutrality.
Okay, so the first speaker, just for your background information, it wasn't really clear. Tom Caballo was the architect, Caballo-Shatko, of that building. And Mike Utzinger is my research partner. He teaches at UW-Milwaukee, and he was the environmental consultant on the building. And it was, at the time it was built, the highest scoring LEED project built to date, and it did actually define carbon neutrality, which is an interesting footnote. Can anybody tell me the difference between net zero energy and carbon neutrality as a concept? So the way, oh yes.
Everything energy can come without using carbon. So net zero is producing as much as we using, but carbon neutral is going to be surface energy.
I like that way of thinking about it, and there's probably something we could spin out of that. That's not the legal definition that I'm looking for, but I do like that. Yes?
Is the difference between, say, buying offsets and then, say, generating all of the energy you need on site and having that amount to a net zero?
I also like that. And all of these things are talking about the same thing. The distinction is actually very, not academic, but legalistic. The building is net zero energy, which means that it is producing as much energy as it is using. So that, and that's annualized. So some days it might be taking energy from the grid, some days it might be putting energy into the grid, but over a year it is balancing. So it's not needing to buy credits. Carbon neutrality, and this is not going to show up on any test, but the way that it was defined by Mike in the lead exemplary performance credit that defined it for the U.S. Green Building Council was defined like the international treaties on carbon trading define it, which is that it's the operation of an entity. So the Aldo Leopold Foundation is carbon neutral, the building is net zero. So that means that suddenly the equation goes from looking at the flows of energy in the building to the flows of energy of the whole operation. Commuting to and from the building, flying to Europe to give presentations, everything that the organization does is balanced. And it does that in a way that I'm not even going to touch on until the very end. Maybe you can tell me at the end of the lecture how the organization balances carbon as exemplified in this building, although not limited to this building. So the prologue to this is that in architectural circles, there's a thing called the 2030 Challenge. Are people familiar with that term? So this was a statement from the American Institute of Architects. Recognizing the clear and present danger that climate change poses to our home planet, in September of 2006, the board of the American Institute of Architects adopts the 2030 Challenge, committing its members to the goal of achieving a carbon-neutral building design standard within 25 years and immediately producing buildings using 50% less fossil fuel energy than conventional practice. So the fossil fuel reduction is the key, and that you are absolutely right about. That's what we're driving at, is pulling fossil fuel use or carbon liberation from fossilized sources out of the operation of buildings. And this definition of carbon neutrality is completely different than the one I just gave you, because it's tied to the building. This is a sloppy definition. The one I gave you is actually, again, that's defined by carbon trading protocols, because ultimately we have to imagine ourselves living in a world where carbon has a price and it's traded on an open market. And so your mission to reduce carbon emissions has an economic incentive behind it. Not there yet. We keep talking about it, we keep inching up to it, and then no. So this was generated, the 2030 Challenge, by Ed Masria, and what's interesting about it is that it built in this idea of incremental reduction. So 60% better than code performance in 2010, 70 in 2015, 80 in 2020, 90 2025. By the year 2030, we should be building buildings that don't use fossil energy, don't liberate carbon. That was a commitment made by the American Institute of Architects. It's been made by many, many mayors and governors. And it's a little disheartening to realize how little teeth these kinds of political commitments that people make. But I will say, I didn't see Texas in this website. I didn't see Wisconsin in the website. But I was just up in Minneapolis. And the state of Minnesota, I mean, I just came from Wisconsin. It's cold there. I'm still not used to not wearing a turtleneck. Minneapolis is a lot colder than Wisconsin, and they are seriously committed to energy efficiency. They have a program that committed all state-funded projects to the 2030 Challenge, And they are on target to meeting that. And they are looking at a very interesting threshold. Right now, everything is better than code by 60%. Everything that's being built, but it's not better by 70%. And 2015 is right around the corner. And everybody in the state government and the energy efficiency community is working hard to figure out, well, it's gotten easy to get to here. It's going to be hard to get to the next step. But everybody's engaged in that challenge. So I just wanted to let you know that even though a lot of this effort kind of fell apart when the economy fell apart, California has adopted the net zero carbon neutrality 2030 challenge. So this project I want to talk to you about comes out of the Society of Building Science Educators. And part of what I want to do is just introduce you to this as a resource. This is a group of teachers who teach environmental technology and architecture, but they have lots of interesting resources that even for engineering students might be useful on the website, spsc.org. And the goal of the project was to take the best of practice, because we were being funded by the AIA, and the best of studio pedagogy, which is the core of what architecture students study, how in a design studio setting to design a building. That typically doesn't involve a lot of deep, sophisticated analysis, but it does involve a strong sense of precedent and gut sense, and increasingly the ability to use simple tools. The project was conceived of as a 4-step project that would end up with us doing trainings all across the world. We got steps 1, 2, and about half of 3 funded. It was very complicated, so the resources are diverse and all kind of half done, but just so you know how it was structured, there were commercial and institutional case studies because, again, we're being funded by the AIA. There were affordable housing case studies because we were also being funded by an anonymous nonprofit that invests in affordable housing research. We were doing case studies of buildings. We were doing case studies of teaching. That 4-quadrant matrix all comes together in this idea of the case study. What can you learn by looking around? We held a lot of big events, brought experts together to talk through the building design. We had groups of faculty at all of these different universities talking about how they teach these issues. We tried to collect those thoughts. We funded several little sub-tools. So here, Pablo LaRoche, Cal Poly San Luis Obispo, Pomona, did inventory of all the carbon calculator tools that are on the web that you can get for free, and what their pros and cons are, and how you might mix and match them to accomplish something. So that tool is up and available. This gentleman, Harvey Bryan, has Harvey ever lectured in this symposium? He's right across the way in Arizona. And so very, very brilliant, active in this field, developed a protocol to develop a benchmark. Now, a benchmark's an interesting thing. When you want to be 50% better than code, it really matters what you define code as, or as the 2030 challenge defined it, current practice, which is often not even as good as it should be, not even up to code. When you talk about carbon neutrality, you don't have to worry about any of this. The goal is really clear. You just want the building to use no more energy than it generates. But that tool is also there on the website. We cataloged a whole series of profiles of studio instruction practices. Very simple. This, if you want to go into teaching architecture, here's a how-to. And if you're an engineering student that just is curious, I brought 3 of those to give away. They include short descriptions of how the studio instructor defines carbon neutrality. Because when we were doing this, which was in almost 6 years ago now, 7 years ago, this was a very new concept. But it's really nothing different than just getting very clear about defining the goal of being in balance. Everything up until this point has been about that, defined in other ways. So it's not like we're talking about a whole new subject here. I love this little thing. All of the faculty contribute 10 things that they think are really critical, 10 mistakes that students commonly make. And so I just highlighted one. If I was to say there's a foundational idea, this is so obvious, but it needs restating. Privileged building performance issues as a parallel consideration to all other design priorities, including client needs aesthetic approach and cost evaluation, i.e., environmental issues are always parallel and never in series. And that's true of all issues in design. And I would think that's true in engineering as well as architecture. The goal is to learn to juggle and to work things and not to privilege one over the other, not to decide one whole set of decisions before another. And then the books have a series of exercises, 2 pages each, very clear instructions, which software was used, what the pitfalls are, looking at different topics that might show up in a design studio setting. Indoor air quality, fresh air, daylighting, passive solar control. These are all things that you engineers are probably learning in a much more nuanced and technical way. Designers are trying to learn how to juggle these things. So they're never very deep, but they're very broad. And then there were a series of building case studies. Commercial institutional, the Aldo Leopold Legacy Center is the deepest case study, and it's the only one that's really even halfway complete. And then the affordable housing. Again, trying to scatter across climates because I'm going to make it sound like all of these solutions are equally applicable to every climate, but you have to know they're not. You have to know that climate and site and the specificity of each individual problem really still drives things. That was a fundamental mistake of architecture of the 20th century, to think that with enough energy inputs we could ignore all of these specificities. The goal is to get in touch with things. The goal of the case study process that you saw the video about was, this is the complicated goal, and I'm going to pitch it to you and say, if you're interested, I can put you in touch with Mike. He developed a spreadsheet approach to simple building metrics. Let's just talk about the physical aspect of the building. Nothing that requires sophisticated monitoring, nothing that requires anything more than a utility bill, but that does require that we know exactly how many pumps and how many fans and how thick the insulation is and exactly what the glazing is, and we can characterize the physical building. You can do that with a set of drawings, in theory. This has turned out to be much harder than it sounds, but the goal was not to have to go in and spend a lot of money. And out of that, generate something that gives you very clear indication that buildings that are designed to be this efficient should physically be different. And the question is how? What are the things that are going to be different about them? My part of this was to try to come up with a common way of what we would say drawing through the problem, representing each of these metrics or the things that we were trying to get at in a common, simple diagrammatic vocabulary so that we could set up a comparative solution. So here we're looking at a simple way to talk about glazing ratio per square foot of floor, fixed and operable. Being able to open a window turns out to be incredibly important. If you can't open a window, you're dependent on a fan. How the walls are constructed. Funny thing about this little building is that it's got 6 different wall types. They threw every different way of insulating a wall they could think of into it. How deep daylight penetrates without really measuring anything, just using rules of thumb. Can we quickly assess the plan to say this is a building that's going to be daylightable, that you're going to be able to turn the lights off? Because ultimately the goal of designing a building that uses less energy is to turn things off. Can you light the building without electric lights? Can you ventilate the building without a fan? Looking at thermal zoning. How is the building structured to protect certain areas and sacrifice others, let things float and let things be controlled? This turns out to be incredibly important. It's stuff that any mechanical engineer from the 1950s knows but thinks about in a different way. The question here is, how can we think about that strategy of saying, well, I might own the whole house, but I'm only going to heat the living room because it's friggin' cold and oil costs a lot of money. Or because simply the goal is to structure the space so that the uses are using energy as efficiently as possible. How does the sun interact with the building? How does natural ventilation interact with the building? And then the mechanical systems themselves, which this building, Mike would say, had an operational manual like a 747. For a small building, it was very complicated, mechanical system. What we're looking at here, for example, is a system of earth tubes. So one fundamental principle that emerges out of this is that traditionally we use air to both heat, cool, and provide fresh air. Air is a really rotten way to move heat around. It's a lot of fan power. So fundamentally, you want to separate out, you want to say, let's just provide enough fresh air to be comfortable, to meet the code, to be healthy. Maybe that's even more than code. Maybe that's 100% fresh air, no recirculation. But we're just going to design this air system to move air. We're going to move heat and cold with water. Much more efficient. Suddenly, you get these, in some ways, systems that we're used to seeing but now applied in different situations. Here, fresh air is being brought in underground through tubes that are in contact with the earth as a way to pre-cool or preheat the air. And to me, what's interesting about this is to recognize that I'm an indoor air quality person. That scares me. That seems like a situation that could produce mold, that we could be drawing air in through a damp, dark, humid environment and then spewing it through the building. And part of why this solution was appropriate here is that this is the sand county. This is very well-drained soil. And so these tunnels are very dry. The other thing they're doing is using solar hot water to reheat the air in the summertime, which seems paradoxical, but they're essentially dehumidifying it by pre-cooling it, dropping it down below the temperature they need, and then heating it back up with solar hot water. So using heat from the sun in the summer when it's available to cool. Isn't that cool? And then finally, it's representing all of these systems, because for an architect, all that matters is how these things spatially fit together. We leave it to the engineers to figure out how to make it most efficient. And there was an engineer, he's actually a Texan, who was part of this project, Ron Perkins. Does anybody know Ron Perkins? So supersymmetry, I believe he's a Texan. He told stories of paragliding and kicking warthogs or something. This was his sport in West Texas. He came into this project. I think he's from Texas Tech. Does that sound like something they would do out there? He came into this project, and the engineers had laid out, now we've separated air and water. We've got radiant heating and cooling in the slabs, and a geothermal system linking this building to the ground. We're using water. It's very efficient. He said, no, too much pump power. He sent the engineers back to the drawing board. They reduced the pump power by 80% simply by doing something that you might have read about in a book by Amory Lovins, which is that you think about fluid flows first, you design the pipes, and then you put the machines in. You don't put the machines in and then design the pipes to connect them together. 80% reduction in pump power just because they were told, no, it's too high. That's the power of knowing how low it can be and then trying to hold to that. That was the goal of the case study, was to reveal these numbers that we should know but we just haven't really looked at. How low can the pump power be to drive a building like this? One of the interesting things that I can understand about it, just being a dumb architect, is that little building that's sort of separate is a little conference room. It's zoned separately, so that because when it has a lot of people in it, it needs to be controlled separately. Also, when it doesn't have a lot of people in it, you can just shut it off. Originally, it was all supplied from the same central mechanical room with the same geothermal lines. And part of what they did was decide, well, that last row of geothermal wells, the lines were too long. If we created a second mechanical room, that might take more space. It might be a little more complicated or costly up front in one sense, but in the efficiency, it paid for itself. And I just threw this in to remind us now that we're doing cooling with a radiant slab as well, which again seems dangerous in a Wisconsin climate, which is a little bit like this in the summertime. Feels like it does here now. It's humid. But again, this is the sand counties. It's out. There's a lot of air circulation. And we're preheating and pre-cooling the air, so we're limiting the amount of humidity inside. And so we can raise or lower the floor temperature without fear of condensation. It's those balancing acts that make it specific to this place and this set of solutions. And finally, there's the issue that Mike started to talk about in the video, which is the fundamental idea here is to say, first of all, let's ascertain how much energy we can generate and how much space we can build given that amount of energy, given our goals to make that space as efficient as we can possibly make it. How efficient can we make it on the one hand? How much energy can we generate? What's the balance there? And because the goal was to draw through every system, I have to acknowledge that, yes, in fact, there was fireplaces. Now, is this a carbon neutrality scheme? This is a tough philosophical argument that the design team wrestled with a lot. It's not fossil carbon, it's terrestrial carbon. It's a shorter cycle. It's coming from the Leopold woods, trees that he planted, just like every piece of this building is. But it is burning carbon. It turns out the winning vote was the 90-year-old daughter of Aldo Leopold, who said they grew up, and if you read the Sand County Almanac, it's all about being out at the shack around the fireplace. So the fireplace became significant above and beyond the issue of carbon neutrality. The other outcome that's physical is the affordable housing guide, and I've got one here I can give away, and I'll just throw out, again, to just keep hammering on different ways of framing this basic proposition that if you want to design carbon neutral affordable housing, just like any other building, you want to start with that assumption. That has to be the goal. You can't inch up towards it. You have to start with that goal. Secondly, you have to design for an architecture without power. You have to think of it like architecture unplugged. It's an acoustical set rather than an electrical set. That might seem like that doesn't involve you. As engineers, I want to say that it does, because you have to convince and work with the architect to make these things happen. Designing for no power is just the same as designing for the use of power. That should get you the first 50%. It's all about the design. It's all about the form, the mass, the orientation, the shading, the insulation. The next 25% is the engineering of the systems to be inherently efficient. This separation of air and water is one fundamental principle that seems to apply through a lot of the case studies we began to look at, didn't finish looking at. Then you produce your own renewable energy on site. Then you, like you were saying, before you turn to having to pull a fast one, which I believe in, of buying credits for carbon, you want to try to generate your own electricity. And then it says go beyond, and I'm going to come back to that point. What does it mean to go beyond neutrality? But I'm going to skip it and just hit the last point. There has to be feedback. Whatever form that feedback is, you have to find a way to learn from your mistakes. That was the opening statement that Tom Kabbalah made, which is the architect's fee does not involve ever looking backwards. Fundamental flaw in the economic proposition of architectural services delivery. We are not paid to learn from our mistakes. There's the website for the Carbon Neutral Project. And I'll come back to that if you can't write fast enough, because I did say I was going to kludge together two studies. So when this died, I kept teaching. And I've had a hobby of looking at LEED Platinum academic buildings, because I have a hobby of beating up on our state to try to get them to build LEED Platinum academic buildings. When I started charting LEED certification of academic buildings, it was just as the LEED process was unfolding, and there was a year here that just really caught my imagination. This is when I started, and there were 16 certified buildings and 6 silver and 5 gold and no platinum. And the next year, it completely reverses. Only 4 certified, 14 silver, 18 gold, still no platinum. But you could feel like the profession is figuring this out. It's getting to the point where, no, it's not good enough to be just certified. Suddenly, we're not just silver or gold. I was waiting for the next big flip. I've been waiting for the next big flip where suddenly platinum is the dominant color. Because I would say platinum is the only color that matters. There's a lot of criticism of lead. It hasn't kept up with the times. Well, in fact, all of these things do change. But the 2030 challenge existed. It was a proposition to leapfrog lead, to set in energy standards that were higher than lead. And it's part of this back and forth between the U.S. Green Building Council and the AIA. What we see here is, lots and lots of buildings are gold, very few are silver certified, and there's been a steady drumbeat of about 20, 25 buildings a year being built to the platinum level on university campuses around the country. The first 10 of those I tried to visit every single one of and do very simple things. So the question, again, I would put to every student looking at this stuff, I'm not very sophisticated. What can you learn by just looking? What's around you? One thing we were able to say is, okay, University of Wisconsin, here's a strategy to build the next building to a LEED Platinum. Here are the points that you would do to get gold and that everybody's doing. And here are the points you would do to get platinum. And by the way, 10 out of the 11 first buildings to do it got that point. What's so hard about that? If 10 out of the 11 buildings could do it, you can do it too. So as of a year ago, my most recent data, 78 academic buildings have been certified at the platinum level. I can tell you that there are 3 in Texas and none at UT Austin. I can tell you that there are 16 laboratories because I've just been given a study on our campus to write a green spec for the next round of laboratory building. And there are 16 labs around the country that are built to this standard. Labs are hogs. Everybody knows that. Labs can't be energy efficient. These are platinum. That means that they're at least in the 50% improvement range, you would hope. And you can tell that many points everybody gets and that some points nobody gets, and so you don't sweat it. Very few labs worry about adaptive reuse of historic structures, although there are 2 up there that did. 2 of the 10 really caught my eye, and they do tell a very specific story that kicks me in the shins. These 2 buildings, Kroon Hall at Yale and the Research and Research Development Building at Northern Northern Arizona State. I'm sorry, I'm blanking out. Both built by the same architect, engineer combination, Europeans. Michael Hopkins and Partners Architects, England, Sir Michael Hopkins, Arup Engineering. That sucks. That's a damnation of the U.S. It's not that we don't know how to do these, but they know how to do them better. They have a reputation for doing them. What are they doing? Well, here is the teaching tool that I evolved at this same time as I was teaching Studio, just like I showed you other teaching tools. I'm teaching studios building academic buildings, so there is a difference. Let's get it up front between big university buildings and small nature centers. I find big university buildings more interesting, but they're fundamentally different energy issues. Masses must be thin. Why? So that spaces can be daylit. Volumes must be vented, so natural ventilation must be accommodated, and the structures must be massive. What do we mean by that? Perhaps concrete, something that is thermally massive, not necessarily physically massive. Surfaces must see airflow. So if you want the thermally massive surface to work, it has to be able to have air pass over it. Apertures must control solar gains. So if you want the sun to come into the building, you also have to say there are times we don't want the sun to come into the building. Envelopes must be thermally broken. If we're going to create an envelope around the building, we want to insulate. We want to first build a building to connect it to the environment, and then we want to create a way to disconnect it from the environment. Air is for breathing. Water is for moving heat. This is what I've been talking about. Swing seasons must have their own logic. It's not enough to say there's summer and winter. There's the shoulder. Oftentimes, The summer and the winter are simple to conceive of. The shoulder is the tough one. Moving air in the direction that it is naturally going. Now, maybe engineers intuitively understand this. Architects do not understand this. Architects will draw representations of air movement that defy the logic of air movement. We know that air wants to flow by pressure or buoyancy, and we can predict that. That is not rocket science. Finally, the photovoltaics must be multifunctional. What do I mean by that? They're expensive. And so this is not quite such a hard-edge rule, but these are design rules. These are rules stated in a way, from my perspective, that are trying to frame the designer's challenge. The challenge is, how do you make that expensive thing do a lot of different things so that you're actually justifying its cost? So, Yale University, Croon Hall, thin plan. That roof is actually one big rack of photovoltaic panels. Yale, New Haven, pretty mixed climate. Pretty cold winters, hot, fairly humid summers. All kind of hugging the humid side of the world. If we use these really simple tools, now these are student case studies, it's thin, it's daylit. There are very few spaces that are completely dark, the gray. There are a lot of spaces that have access to light, but perhaps by this rule of thumb, it's further away than 1.5 times the height of the window. It's got a phenomenally well-insulated envelope, 4 inches of insulation, rigid insulation outside of a masonry unit, backup wall. I don't have the dimensions with me on the top, but it's at least 8 or 10 of rigid insulation again. It's a thermally broken envelope. It's a very well shaded envelope. This is a very traditional building with thick walls. Even though the walls look thicker than they are, those stones are articulated so that they're fins and the glass passes behind them, kind of a play on the idea that they're Gothic and thick. But they act as shading fins. So the walls protect the glass from the sun. It's got a lot of operable windows. You look at it, you can see both sides, every floor opens up. Most spaces have clear paths for air movement. Only the stairwells aren't naturally ventilated in any kind of clear way for obvious reasons. They're fire stairs. And it's thermally massive in a way that connects that mass to air movement. What Hopkins does, typically what's the European model, I would say, is the idea of using a raised floor as a plenum to distribute air through buoyancy, much less fan power than distributing air through ducts. And the backside of that benefit is that now you have a concrete ceiling and not a concrete floor. And so the ceiling is where all of the heat is rising. And the ceiling is a thermally massive surface, and so it's absorbing the heat of the lights. And as air is drawn through the building, it's absorbing the heat of the air. And so it really is engaged as a flywheel. And finally, that the PV systems are sized in somewhat accordance to the loads. This building has a 2.8 watts per square foot gross building area. Aldo Leopold has 3.2. So it's not so different. This is a 4-story building. This is a very hard, typically you'd say 1 to 2 stories you can power with the roof. Here, the roof is so extensive and so from wall to wall that they're close to carbon neutrality. Now this building, for a reason we will discover, we haven't really gotten data on. I doubt it is actually carbon neutral, but it is heading in that direction. Its intention was to be that. The dark windows are the toilet cores. Those are evacuated to solar hot water collectors, so they're heating water for the bathroom cores in the bathroom cores. It's a very elegant, understated solution. And my favorite integration, I said the PVs must be multifunctional. Here the PVs are a translucent sunshade over the skylight, bringing light into the center of the building. So they're acting in 2 ways. They're both generating power and acting as a shade by the fact that they're intercepting the sun. So we see that list again. What that list doesn't include is the fact that this does have a geothermal field in the foreground here. So this building is not only thermally massive, it's connected to the thermal mass of the Earth in part of its mechanical strategy. But what we really don't see here is that this building is not just a building. It is a massive piece of infrastructure that replaces and connects underground tunnels that serves this whole quadrant of the campus. And so this is the reason why this building is hard to get energy data on, because it is not an isolated object. It is part of a larger system. I would argue that that's what makes it great, because it's leveraging its own building construction to solve larger problems. I don't have any evidence that it actually, it is independent of the campus steam grid, for example. So it is energy independent, but it's not physically independent, so there's heat that's not being monitored, leaving out that loading dock. Finally, and I'm going to do this very quickly, I appreciate the warning. The second building I mentioned was Northern Arizona University. Now, this is Arizona. It should be hot, but it's friggin' cold. It's up at about 7,000 feet. It's a 7,000 heating degree day climate, almost no cooling load. And every day and night, hot, cold, hot, cold. It's a desert, high desert. It's a thin plan, we know that. It's fundamentally a greenhouse. This is unique to its site and climate. This space is fundamentally a south-facing greenhouse with a thermally massive floor and back walls. And if you look at the design evolution, the English were convinced that the greenhouse could be all glass all the time. And what the design has done is throttle that down to the appropriate balance between insulating, controlling the sun, and having solar access. So the greenhouse was glazed on the roof and much taller than the building. Now the greenhouse is just the height of the 3 occupied floors and not glazed on the roof. And it's very well shaded. It's got operable windows at the top and the bottom, driven by a computer that ventilates the greenhouse independently of the building so that it is very easy to control. It's a blessing of a desert climate. And there's something other interesting that shows up in this kind of analysis. The top floor, the red windows stop. I'm taking time, but I got to know, does anybody have a guess why the top floor, the red windows would stop? Suddenly there are no red windows on the right-hand side of that drawing. There are no operable windows. Because the top floor of this building, where the fume hoods are, is a level 3 biohazards lab. I don't know if I have the classification right, but this is where they do testing of anthrax for when the president gets a letter that has anthrax threat to it. This is where it goes. So that is a lab that is an energy hog. There's no way that that lab is not operating 100% fresh air at a very high volume all the time, and it's built like a submarine. So I talked about the fact that the glazing is operable, and there are shades that are mechanically driven, that the wall is very well insulated. Here, it's got chopped up denim as a cotton batt insulation on a 10-inch stud, which thermally seems like a bad idea to have the metal stud there, but then it's got another 2 inches of rigid insulation on the outside. It's a very well thermally broken wall. Daylight and windows that are controlled by a little green light that tells you it's okay to open the windows. It's okay to, no, it's too hot, too cold, close the windows. It's very well daylit. It's very well naturally ventilated on the floors that accept the lab. And it's thermally massive. The surfaces of the concrete are open to air circulation. It has a raised floor, so the air is being ventilated by displacement ventilation. But the PV is not integrated with the building, because even to just get 20% of the energy load of this building, this is a field that's almost 10 times larger than the other fields we've looked at. And it's still only 20% of this load because of the laboratory load. That's a philosophical question for designers. Is that part of the same project? That was a big fight with the U.S. Green Building Council. They would say yes. It was part of the same budget. It was part of the same campus. Those two things are associated. I would argue that's absolutely true. And finally, there's something else that you should know, that every time you design a solution to solve one problem, you create another. This European model, high mass buildings, especially with a glass and concrete space, has horrible acoustics. And so all of that railing we saw is actually acoustical batting filled with denim to create some sort of acoustical soft surfaces in there to take what you're trying to make as a thermal environment and not turn it into an acoustical nightmare. So my list again, I won't elaborate it. I'm just making my last point, which is that I've been waiting for this flip where suddenly we go from gold and just a few platinum. This building makes that irrelevant. This is the Sears Building on the UBC campus. This is a living building challenge building. This is a living building challenge building, meaning generating its own power, capturing its own water, treating its own waste, not just better than code, but net zero in every category it can be. It's a large piece of scientific experimentation equipment. And how does it get to net zero? It's very clever. It gets to net zero by recognizing that there's a 1970s laboratory next door that has very inefficient fume hoods but has no plans to renovate them. It says, hey, let us steal your waste heat. We'll take it into our building, we'll heat it, and we'll return it to your building in a form that you can use. So it is physically breaking down the idea that the building itself is what matters. The building is now reaching out and developing a symbiotic relationship with another building to say, let's be both more efficient by my investment. Which brings us back to the Aldo Leopold Foundation and another issue that hangs there. This is the very beginning of a PhD dissertation, so we don't have any numbers yet, but this student is looking at the embodied energy in the building. And even though the building is a wood building, there's a lot of concrete, and concrete is the highest embodied energy material of the building. What we're going to find is that there's a lot of energy embodied in this concrete. So you've got a building that is using no fossil fuel energy, but generated a lot of carbon in the making of it. Should that matter? For the architects, the idea that they could make retaining walls out of stone because the stone was local and actually already quarried, and all they had to do was get a backhoe to drag them over and stack them up, seems like a win-win. It's suddenly a lot less energy intensive than the concrete retaining wall would be. Which takes us back to the ARD building. The most interesting thing about the construction of this building is not that we had European contractors working in Arizona because it was all done by local people, but it was 40% fly ash. Why would that matter? 40% fly ash is an industrial waste, comes out of coal-fired processes to substitute for Portland cement. So it's much less embodied energy in the cement that makes the concrete hard. And getting up to 40% is hard. Fly ash is actually a better cement than Portland cement in the long run because it takes a long time to cure, but it cures quickly. It's sticky, it's hard to work with, but when it cures over time, it's very, very hard. So 40% is a very high content. Why would they go to this trouble to use a mass that was less carbon intensive? So which takes us back to the Sears Building, which is not a concrete building at all. The first academic building we've looked at, this is engineered heavy timber framing in a 4-story academic university building. Why? Well, partly because it's British Columbia. It's a local resource. Partly because now it's not just a low-carbon structural material, it's a carbon sink. This is a material that is taking carbon out of the atmosphere and locking it up for the life of the building. Which takes us back to the Aldo Leopold, which the whole thing was built out of the Leopold forest. And I asked the question at the beginning, how does the building become net zero and the entire organization become carbon neutral? The entire organization becomes carbon neutral because their estate is to manage the Leopold forest. And the Leopold forest is managed for carbon sequestration. And this is allowed under international carbon trading protocols. It's selectively harvested. The harvested wood is used for long duration purposes like building buildings, so that it's not cycling the carbon. It's fixing carbon and taking it out of circulation. And by doing that, by managing a carbon sequestration forest, they are covering the carbon budget of operations. So, there's my list, and I would add to that two thoughts. Forget the idea that the building should be neutral or independent. The building is part of a larger system. You should be looking for opportunities to glom onto other larger systems. This is where I think the future is, to think about systems sharing energy across boundaries, also sharing water. And secondly, that this idea of using thermal mass to your advantage is good, but not if it's carbon intensive. The structure should be a carbon neutral or even a sink. So, that's my concluding slide. Thank you for your indulgence. Okay. Yes. You take the mic around. That makes sense.
Hi, thanks for being here. So, speaking of buildings being part of these larger systems, I have a question for you about life cycle analysis. Steve Wozniak, the co-founder of Apple, was in town in Austin this week, and he made an interesting remark about energy efficiency and what he perceives to be a little bit of a false promise when it gets to the extent that you're doing this to the nth degree. And the way he explains it, it's any amount of energy that you're saving in a situation like this, that money that you have saved, that does not go out of circulation. Someone is going to take that and they're going to spend it on something else that is energy or carbon intensive. So in the context of a university campus, facilities is going to get a new van. They're going to buy a couple more computer monitors. It's not like they just retire that. So what would you say in response to that in terms of like the long-term life cycle analysis of what happens after we build an energy efficient building?
There were some policy people in here, right? This is a policy question. Without thinking too hard, I would say yes, there is a trap, and there's a word for it, that the more we save, the more we do other things. But fundamentally also, no. If we as a society decided to limit or by resources being restricted, we became more efficient, it doesn't necessarily mean that, if, for example, there was a true restriction on resources, we would save them, and we still wouldn't have them to spend. We would save them because they were not there to be spent. Can we set up rules where we develop economically and buy new vans without contributing the same amount of carbon to the atmosphere that we would have if we'd just been wasteful in the first place? I would say absolutely. I would say otherwise, what's the point of thinking about design as a progressive activity at all? It's one thing I would point to is that it is true that energy prices were going up, and they leveled off in the 80s. And in a way, that took out a lot of steam out of the environmental movement. But why did they level off? They went up because of OPEC in the 1970s, and they leveled off because of the response to OPEC was to build in a lot of efficiency in the economy that hadn't existed before. In a lot of ways that we didn't see, in a lot of ways that were big, simple tasks that didn't affect architectural design. But the point is that you can bend curves. And so I think it's not a zero-sum game. There has to be, I think, the vision of a way, and it means a more comprehensive understanding, perhaps, to say, yeah, if we're going to restrict something here, we're not going to let it leak out here, or we're going to channel it in ways that are hopefully not just limiting the damage, but beginning to create positive change rather than negative change, or not just being less bad, but actually being good. That's, I think, a fundamental design goal that is hard to define, but I'd challenge you to think about that as the response, that there has to be a way to say that we can re-engineer things, and I think it's a matter of making the system boundary big enough that we see the whole pie, so that then we do set rational goals and structure things so that they move in the positive direction. I'm rambling, but I can't believe that it's that simple as to say that everything we do leads to, we build another highway, we get more cars. That's the paradox. But we could just say no more highways, let's build mass transit. Yes?
I spoke regarding kind of the current, and it's always been that way, where architecture doesn't look backwards. The first thing to get cut on a project from an engineering standpoint generally is the controls or the ability to actually regulate or capture the energy data. That's why none of this data really exists. Even in LEED buildings, it's been a huge thing about LEED, and they are changing it in the new version. But how do you see architecture kind of starting to looking back and therefore looking forward?
That's another complicated question that I'm not really the expert on, but I would say that the state of Minnesota, for example, in those state buildings, the Center for Sustainable Building Research does post-occupancy evaluation studies. They set up monitoring, and so it's a mandate that some information feed back into the system. Architectural delivery methods are changing, and I think LEED has been part of that conversation to drive the idea of performance to the foreground and to get corporations that operate large portfolios of buildings to realize that, yeah, it's an economic issue, that having feedback is in their interest. So I think there are lots of different ways we could talk about it changing, but I think it's just a matter of realizing that there's value in it changing. And then the contractual relationships, all of those things have to change. It's not just simply that we're going to suddenly do it. We're going to do it because there's somebody else is going to step in and do it for us, or there's another motivation or another player or another structure that pushes things in that direction.
We have time for one more question.
Sorry.
This is actually partly two-pronged. One is that it seems that too loud, sorry. Zero energy technology or zero energy designs are very difficult to implement in existing buildings, which are a large part of the building stock. And if you're looking, this is part two, if you're looking at zero energy communities or neighborhoods, as you've discussed, like a larger network would be more efficient. How can we go about ensuring that these neighborhoods and designs that urban planners do put together don't become, are planned correctly so that they're not ignored and abandoned because they're not designed for the right community? That makes sense?
Again, lots of different issues that you bring to bear on that kind of question. First, about the existing building stock. And that's an interesting thing that's well documented, at least as a polemic, on the Architecture 2030 website, that yes, the vast majority of building stock is built, but yes, there is an incredible amount of churn in our economy, and from what I hear about Austin, there's an incredible amount of churn here, that building stock is renovated systematically over time, and if you look at that, Ed Masria will make a very compelling case that if we set targets, now they might be lower targets than for new buildings, but if the targets similarly ratchet down, that you will eventually catch a large majority of the building stock because it will be renovated over time. And I think this idea that they're working on, and I think of it, or I know of it through the Sears Building, through UBC's work, but it's a more ubiquitous idea of building district systems and thinking in district scale ways and sharing flows. I think that has real opportunities in existing environments. So the Sears Building itself was glomming onto a 1970s era laboratory building in its immediate adjacency. So, I mean, I think there are ways that building larger scale systems might be able to be retrofit to existing conditions. And then to talk about larger scale developments as a whole, I think we have to understand the physical parameters that make for naturally low energy development patterns. Solar access and density and transit, and it is, again, not thinking about the building but thinking about the system, that we understand those things pretty well. It is just a matter of building those form codes into neighborhood development, for example. So I think it's quite doable. And there are many great examples all around the world of communities that have been built to very high energy efficiency standards. And my point here, to reiterate where I started, was that at least half of that is solved through the physical design. It's the relationship of the building to the environment, how well it's connected and how well it's able to disconnect. Okay.
Thank you so much, Jim.
Thank you. If anybody wants these, I don't want to carry them back.